Hello all of you. Today we will discuss one of the critical topic of subject antenna and wave propagation. This is the subject that is we study in the third year, which is one of the subject which involved electromagnetic field theory and antenna wave propagation. But today we will discuss about the sky wave propagation, how the wave is going above in the sky and reflected back by the ionosphere to reach the earth back, and the mechanism that drive this propagation and the critical frequency and maximum usable frequency as well. So we will start by discussing the topic what is wave propagation. So when the wave propagation is basically divided into three categories, as we will discuss in the previous lectures. That is ground wave propagation, space wave and sky wave propagation. So in the case of sky wave propagation, the maximum frequency range that is used for the communication is from 2 megahertz to up to 30 megahertz, and this is the type of electromagnetic wave that is penetrate into the sky, different layers of the ionosphere, and reflected back by the ionosphere to the earth, so that the wave is reached to the earth. The ionosphere is lying up to 30 to 250 kilometer. 30 to 250 miles above the surface of the earth. So the wave that is going in the space get reflected by this space of the earth to the space of the atmosphere of the earth to the earth back, and this propagation is known as sky wave propagation. Now the layer of the atmosphere is like this. One of the layer is troposphere, then stratosphere, and then ionosphere. So in the case of stratosphere, the space wave communication is possible in the stratosphere, which is a very lower part of the ionosphere, as we can see over here. So this is the layers of the ionosphere. The lowermost layer is the stratosphere, and this is troposphere. This is lie up to 10 to 15 kilometer from the surface of the earth, and then above this there is a layer known as stratosphere, which is up to 50 kilometer. From 50 kilometer to 400 kilometer above the earth's surface, the layer lies in the form of D layer, E layer, F1 layer and F2 layer. So these layers are stacked into a category that is named as ionospheric layer. The name of these layers are varying because the density of the electron that lies within these layers are going to be changed, and it is also changed according to the time of the day. Like in the daytime, when the sun is very high in the sky, the received ionospheric radiation from the sun as well as from the sky, having large amount of high frequencies, microwave, ultraviolet wave, X-rays, gamma radiation, and due to these radiation, in these layer, the electron, the atom get ionized and the electron density is increased. So at the topmost layer have the highest electron density, and the bottom layer had the lower electron density. So this is the structure of the ionosphere, and when the sky wave is penetrated into the different layer, due to the different refractive index of the layer, the wave get reflected back to the earth by the ionosphere. Now this is the different layer architecture of the ionosphere. E layer lies between 90 to 130 kilometer and reflected the frequency up to 20 megahertz, while F layer is from 140 to 400 kilometer. This is the topmost layer of the ionosphere, and it is divided into two categories, F1 and F2 layer. In the daytime, it is converted into two different layers, F1 and F2 layer, while in the night time, these layers are going to be merged, F1 and F2, and became a single F layer. And it is used for long distance communication because this is the highest layer, so generally used for long distance communication. Now, as we see in the previous discussion, that the the refractive index of the different layer going to be changed as the electron density change. So we will discuss how the electron density or refractive index is depend upon the number of electron in a particular layer. Let's suppose if we fire an electric field, that is wave having the electric field vector E is equal to Em sin omega t, as we can see over here, Em sin omega t, and to the layer having the electron density n, which is having the number of charge carrier, which is basically the electron having the charge E and the mass m. So the force over this this electron is equal to F is equal to E times of E, where E is the amplitude or the electric field that is fired into the space. So the force acted on the electron F is equal to E into E. Now we also know that the force on a particular matter is equal to mass into acceleration. So if we see mass into acceleration, that is change in velocity, so m dv over dt is equal to minus E into E. So this dv over dt is calculated as minus E by m, where E is the electric field and dv is equal to Em into dt. Now if we integrate both the side, integration of dv, and here is the integration of this thing with respect to time t. So this electric field is now time dependent, as we can see over here. The electric field is the time dependent vector, that is equal to Em sin omega t. So over the integration of this vector, we get the electric velocity of the electric field is equal to v times of E m sin cos of omega t divided by m omega. Now this velocity create a current density due to the movement of the electric charge. So the current density having two component, either drift current velocity or drift current density or diffusion current density. So here we have the drift current density having the formula J is equal to minus n E into V, where n is the electron density and v is the velocity of the electron. Now we already calculate the velocity of the electron in the particular layer having the electron density n. So J is equal to minus n E by m omega Em cos of omega t. This is equation number 4, and now we can calculate J is equal to this. This is the drift current velocity. Now for the diffusion current velocity, we know that the diffusion current JD is equal to del D over del T, or displacement current JD is equal to del D over del T, where D is the flux density. So this D is equal to epsilon naught times of E. Now putting this value, putting the value of electric field Em sin omega t and differentiate it with respect to time, we get JD is equal to this. Now we have the total current density, that is the sum JT, that is JD plus JE, that is epsilon naught Em omega cos of omega t minus NE square by m omega Em cos of omega t. So now now take out the common part and we have the electron current density, that is equal to given by this equation. And here we can see the current density is highly depend upon the number of the electron in the particular layer, or we can say the electron current density, because E is the constant that is having the value. This is the charge on the electron, that is 1.6 into 10 to the power 19, mass of the electron, frequency over which the wave is transmitted. So now if we have to calculate the relative dielectric constant, because the refractive index of the medium is depend upon the dielectric constant of the material of the layer. So we have to calculate the relative dielectric constant of the layer. So if we compare the equation number 7 to the equation number 6, this is equation 6 and this is equation 7, we have this epsilon naught is modified to the value of epsilon naught minus NE square by m omega square. So here the refractive index of the layer, relative dielectric constant of the layer, epsilon is equal to epsilon naught minus NE square by m omega. So if we compare these two equations, we have epsilon is equal to now this value take the epsilon naught common, we have now this value. So the relative dielectric constant is nothing but the ratio of the dielectric constant of the layer divided by standard dielectric constant, that is epsilon naught omega by epsilon by epsilon naught. We have 1 minus Ne square by m omega square into epsilon. Now the refractive index of the layer is given by C by V, where C is the velocity of light and V is the velocity of electrons. So this is equal to under root epsilon into epsilon mu into epsilon upon epsilon naught into mu naught, and this is equal to mu naught mu r epsilon naught epsilon r divided by epsilon naught epsilon r. Most of the things are got cancelled, and we have refractive index n is equal to under root of mu into epsilon. Now mu now for the case of the atmosphere, we have mu having the value that is almost equal to 1. So if we put mu r is equal to 1, we have refractive index n is equal to under root times of epsilon r, or n is equal to under root times of epsilon r, or this is equal to 1 minus Ne square m omega square into epsilon. Most of the things are constant over here, as E, m and epsilon, these are constant. So after putting the value of these variables, and omega is equal to 2 pi of f. So by putting these values, we have the refractive index in terms of frequency and electron density of the layer. We have n is equal to 1 minus 81 n by f square. So now we will see that the refractive index of the layer is directly proportional to electron density of the layer, and this is 1 minus of electron density. So as the electron density of the layer increases, the refractive index is going to be decreases. So the top layer of the ionosphere, that is F layer, having the refractive index is very small compared to the bottom layer, that is D layer of the ionosphere, because having the this layer having the electron density is very low. So now the mechanism of the wave propagation is like this. We have the refractive index of the layer given by this formula, and it is highly dependent upon the n. As the ionosphere is having lot of ionization, so electron density is very high. So when the wave is going from stratosphere to ionosphere, this is actually behaving like it is going from denser medium to rarer medium. So when the wave is going to be from denser medium to rarer medium, the wave is going away to the normal. As we can see over here, the incident angle in the denser medium is I, and the refracted angle in the ionosphere, that is a rarer medium, is going to be large in compared to I, and it is depend upon the number of electron. Now if we see that there is multiple layer in the ionosphere, when the wave is transmitting from this antenna, this is the rarer medium, this is the denser medium, the wave is going away from the normal, from this layer, then it is penetrate to this layer and going away again from the normal, and at a point come where the incident angle is so low that a total internal reflection is performed over the layer number 4, as we can see over here, and due to the total internal reflection, the wave is going to be reflected back and received to the receiving antenna. So the distance between the transmitting antenna and the receiving antenna, where no wave is reflected back to the ionosphere, is known as skip distance, while the wave that is coming back to the antenna is known as the sky wave, that is reflected back by the ionosphere. If the frequency of the transmitted wave is changing, it may be reflected from the higher layer of the ionosphere. So the skip distance can be depend upon the frequency as well as the angle of incident where the wave going to be penetrate into the ionosphere. There are certain frequency that is related to this communication, like critical frequency. Critical frequency is the frequency that is free from the angle of incident. As we can see, the angle of incident play an important role in the sky wave communication. But when we remove the effect of the incident angle, so when the wave is going directly perpendicular to the ionosphere and reflected back by the ionosphere to the same antenna, then the frequency which is going to be reflected by a certain layer is known as the frequency of critical frequency of that particular layer. Like if a wave is reflected back, like if the incident angle of the wave is 90 degree, that is normal to this layer, and it is reflected back by some layer to this layer and having the frequency, let's suppose 2 megahertz. So when the wave is reflected by N4 back to the transmitting antenna, then the critical frequency of that N4 layer is given by 2 megahertz. That is the frequency of this wave, that is which is going to be penetrate vertically into the ionosphere. So this is the critical frequency, and we can calculate the critical frequency of the different layer by using simple formula. As we know that n is equal to sin I by sin r, refractive index, and it is equal to under root of 1 minus 81 n by f square. So if we put the incident angle I is equal to 0 over here, this complete thing became 0. So we have under root of 1 minus 81 n max by fc square, and this case, as the angle of incident is 0, the wave is going to be penetrate directly at the frequency at that direct wave is known as critical frequency, represented by fc, and the layer having the maximum density which is going to be reflected back to the earth is represented by n max. So it is equal to 0. So if we calculate this thing, then fc is equal to under root 81 into n max, or fc is equal to 9 under root n max. So the critical frequency here we can see it is directly depend upon the under root of n max, that is the maximum electron density of the layer. As we already discussed, in the daytime the electron density is high for the same layer, while in the night time, when there is no sun, there is no rays that is coming from the sun to ionize the air molecules. So we have the electron density at that time is minimum. So in the daytime, especially in the noon time, we have the n maximum, and we can calculate fc is equal to 9 under root of n max, and it is depend upon the electron density of the layer at that time of the day. Next is the maximum usable frequency. The maximum usable frequency is again the it is dependent upon the different time of the day as well as the angle of incident, and this is the maximum frequency that is going back to the earth when the angle of incident is having the value greater than 0, and this kind of frequency is known as the maximum usable frequency. So we can calculate the maximum usable frequency when the refractive angle r is equal to 90 degree, that is the wave is going to be going back to the earth. So n is equal to sin I by sin r, where sin I is equal to 90 degree for this time. So the term became sin square I is equal to 1 minus 81 n by f square, and upon calculating these values, we have cos square, or in terms of critical frequency, we have maximum usable frequency is equal to fc times of sec of the incident angle. So this fc is nothing but 9 under root n max. So now the maximum usable frequencies depend upon the two factor. First, in the incident, the electron density of the layer over which the wave is going to be reflected, and I is the incident angle of the ray, and this law is known as the second law. So maximum usable frequency for a particular layer is equal to critical frequency times of secant of the incident angle of the ray. Now this is the structure how the sky wave propagation is take place. So as we see, if the wave having the incident angle very high and having a great frequency, it is going to the space, as you can see over here. If we see the wave number 1, that is going to be reflect from the ionosphere and land away from the from the transmitting antenna, because the angle of incident is very high and the wave is reflected by away from the large distance. So the skip distance is very large for the ray 1. The ray 2 is again reflected wave as we increase the angle. So for the minimum angle which is going to be reflected back to the earth, and the distance between the transmitter and the receiver at that time is known as the skip distance. The frequency above this, if we increase the incident angle, we have to go to the upper layers of the ionosphere, so it can increase the skip distance and the range of communication as well. This is the different path that is followed by the rays, as we discussed in the previous slide. And there is a virtual height concept is there. As the wave is going to be reflected from the ionosphere layers, if we see, we projected the path of the rays, we can see the rays is going up to this point and back, reflected back. So the actual height is smaller than the virtual height that is traveled by the wave in the ionosphere, because it is going to be reflected by a certain layer. So this height is known as the virtual height. So thank you for this lecture today. In this lecture, we will discuss many things like critical frequency, maximum usable frequency, how the sky wave is highly depend upon the electron density of the different layer, structure of the ionosphere, and the virtual height. So thank you for that.